Okay. Hey everyone, I'm Kartik, and today we'll be going over the Zelha tree problem. So let's just read the problem first. So Zelha tree says, given a list of numbers x, a Zelha tree for the list obeys the following. The Zelha tree has the min heap property, so every value is less than or equal to its children. And an in-order traversal of the Zelha tree visits the nodes in the same order as the list. Okay, so let's just revisit what an in-order traversal is again. So an in-order traversal means that we go to the left child first, then the root, then the right child. Okay, and what that also implies is that the leftmost item on the tree will also be the first element of our list. Similarly, the rightmost item of our tree will be the last item in our list. Okay, so now it says, for example, given the list 9, 3, 7, 15, 1, 8, and 12, the corresponding Zelha tree is shown below in part A. Okay, so let's just verify that really quickly. So first, does this fulfill the min heap property? Okay, so 1 is less than both 3 and 8, so that's fine. 3 is less than both 9 and 7, okay. And 7 is less than 15, and 8 is less than 12. Okay, great. So it fulfills the min heap property. Now what else do we need to check? The in-order traversal is the same order as the list. So, as I said, we start off on the leftmost element of the tree. So that's 9 in this case. So we have 9, then we have 3, because that's the root of 9. Then we have 7, and then 15. So far that's all matching up this list. We go back up to the root of the entire tree, which is 1. We go to its right child, which is 8. 8 has no left children, so then we actually write 8 down in our list, and then we write down 12. Okay, perfect. So this matches up exactly how this list matches up. So that's a valid Zelha tree. Now let's do the same approach for parts B and C of, well, part A. So we first figure out if this is a min heap. So 3 is less than 4 and 5. 5 is less than 6 and 7, and 7 is less than both 8 and 9. So the min heap property is good. Okay, so now we need to check the in-order traversal. So an in-order traversal will first visit 4, then there's nothing else left on the left side of the root, so we visit 3. Then we visit its right child. But there is a left child to 5, so then we visit that first. So 6. Then we visit 5. Then we go down to 5's right child, and then its left child, which is 8. Then we go to 7, and then we go to 9. Okay, and that matches up. So it's 4, 3, 6, 5, 8, 7, 9. So this is valid. Perfect. Now we have one last part for part A. Let's just check if this fulfills the min heap property first. So 1 is less than 2, 2 is less than or equal to 2, and 2 is less than or equal to 2, which means this is a valid min heap. Well, the min heap property is fulfilled, rather. Now, let's check if the in-order traversal gives the same order as the list. So there is no left child to 1. So we start off immediately at the number 1. So our first number is 1. Then we go down to 2. 2 has no left children as well, so we put 2 in. Then same thing applies, 2 and 2. And that's the same order as this list, which means that this is a valid Zelha tree. Okay. Now we want to determine the Zelha tree for the sequence 8, 3, 9, and 1. So it may be sort of hard to figure out how do we start this part of the problem. Well, we do know one thing, that the zealotry has to fulfill the min-heap property. And this means that the smallest element is necessarily the root of the tree. So that means, let's just find the minimum element of this list first. In this case, it's 1. Now, what else can we say? Well, we know that the second smallest child, or the second smallest element of the entire list, will be a child of the root. And I think that can be verified fairly easily. But the question is, which side is the second 3 on, which is the second smallest element? Well, we have two options. It can be either on the left of 1 or on the right of 1. Since we know that this list has to be the same order as an in-order traversal, and we know that left comes before right, we know that 3 should be on the left of 1. So now we'll make this 3. Now we have 2 elements left, 8 and 9. Let's just find the minimum element again. That would be 8. So 8 we know comes before both 1 and 3 in an in-order traversal, which means that it has to be to the left of 3. Since there's no other element, we'll just make it the left child of 3. Now let's look at 9. 9 is to the right of 3 and to the left of 1, which means it comes after 3 in an in-order traversal and it comes before 1. The only area where that can happen is the right child of 3, so we'll make 9 the right child of 3. And that's a valid zealotry. We can verify this just by saying, is it a min-heap? Okay, it's 1, 3, 3 is less than 8, and 9, so it's valid min-heap. Min-heap property is good. Now let's check the in-order traversal, just a sanity check. So we go 8, then we go to its parent, which is 3. We go to its right child, which is 9. And we go to the overall root, because there's nothing left, 1. And this matches that. Perfect. So now, let's do part C. They wanted to draw a valid zealotry corresponding to the sequence of 13, 7, 2, 1, 5, 16, 8, and 9. Okay, so this sequence is a bit long, and it can be sort of daunting. But let's try to break this down how we would any normal, part B, for example. So in part B, we found the minimum element, right? So why don't we just try to find the minimum element again and see where that takes us? So we start off finding the smallest element, which in this case is 1. Okay, now let's find the second smallest element. In this case, it seems to be 2. So where would 2 go? Well, 2, as we said earlier for the previous part, 2 is on the left of 1. This means that it has to come before 1 in an in-order traversal. And for it to come earlier than 1 in in-order traversal, it must be the left child of 1. Note that we do know that 2 will have to be the left child because we know necessarily that everything below 2 will be less than or equal to 2 because 2 is the smallest element besides 1. Just try to verify that for yourself as well. Okay, now let's find the next smallest element. That's 5 in this case. So 5 would be the right child of 1 for the same reasons why 2 is the left child, because it comes after 1 in the in-order traversal. Okay. Now, what's the next smallest element? It seems to be 7. 7 comes before 2 in an in-order traversal, so it must be the left child. Okay. The next smallest child? It seems to be 8. 8 comes after 5. So that means that 8 should be the right child of 5. What's the next smallest element now? 9. So 9 again comes after 8. So 9 is the right child of 8. Now we have one more element, 13. 13 is to the left of 7, which means that it should be the left child of 7 because it comes earlier in the in-order traversal. Another note is This also fulfills an earlier statement that the leftmost element in the list would also be the leftmost element in the tree. See, it's right there as well. Now we have one last element, and that's 16. So where should 16 go? It comes between 5 and 8 in order traversal, which means that it's to the right of 5 and to the left of 8, which means that it should just be the left child of 8. And I think that should make sense. Let's just verify that this is a min heap. So 1 is less than 2 and less than 5. 2 is less than 7. 7 is less than 13. 5 is less than 8. 8 is less than 16, and 9. Now let's do an in-order traversal really quickly. So we have 13, 7, 2, 1, 5, 16, 8, and 9, which matches perfectly with our list. Okay, so A through C is now done. R is. But anyway, I'll see you for part D.